Wow, guys, that's so creative. I bet Lingel laughed and laughed and laughed.
He laughs at the talking Halloween. He does. He goes.
I've heard Lingel laugh.
Have you?
Yeah. Like it's more of a chuckle.
Yeah.
It's more of a chuckle. I've never heard him have like a good old belly laugh. Like it's hard to
I haven't
picture.
heard anyone ever have a good old belly laugh.
What? Oh, well then, come on. Yeah, I've been known. Okay, so yesterday you should have begun thinking about heat. Thermochemistry is the study of heat in chemical reactions. That's the first sentence on the page. I just read it. So thermochemistry comes, of course, from chemistry, which is the study of chemicals.
Which is heat.
And, of course, thermo from thermos, which is Greek for heat. Heat. So thermochemistry is heat chemistry. Makes perfect sense. Chemical reactions just about always involve heat. Just about always. Because when a chemical reaction happens, these usually involve collisions. They must. I mean, by definition, it involves molecules coming near one another and interacting such that bonds are broken and new bonds are made. Now, the first thing to understand is that since they require collisions, they require heat to happen. If you went to absolute zero, where there was no heat present, you could not have any chemical reactions. Does that make sense? You need these things to knock into one another. If nothing's moving, you can't have chemical reactions. Yes, ma'am.
Would it still be a chemical reaction if you made them move without them creating movement on their own?
I don't really know how to answer that. I don't know. I mean, we're dealing with something that isn't physically possible, right? So I don't know.
It's like saying trying to get this boat to move, but it's just
Yeah, well, I mean, now we're not talking about chemistry, right? Now we're talking about movement and physics. But just about every chemical reaction will have a net change in heat, which is to say this. Inside a chemical bond is energy. When that bond is broken, that energy is going to be released. It's got to go somewhere. So chemical bonds store energy. It's a form of potential energy. And when that bond is broken, that energy is released as heat. But don't forget, chemical reactions don't just involve breaking bonds. They also involve making bonds. And when they make those bonds, they have to take in no energy, yes, right? And they have to store that energy in those bonds. Now, it is possible that those are the exact same amounts of energy, right? It's possible that you break a bunch of bonds, it releases energy, you make new bonds, it's the exact same amount of energy taken in, and there'd be no change. But that's pretty rare in chemistry. In most cases, some bonds require more energy than others. So either you will have a net release of energy, there'll be more energy released than taken in, or there'll be more energy absorbed to make new bonds than was released in the first place. If we release a bunch of energy, what is going to happen to the surrounding environment? To the scientist watching, what would we observe? We do a reaction, it releases a lot of energy and absorbs just a bit to make new bonds. What would we experience as the scientist? A whole bunch of energy has been released. How are you going to observe that? Sure, but we're talking about thermochemistry. So in terms of heat, what will you observe? Again, we're talking about heat. Like that's true. That could be a byproduct, but heat itself. Good. So the temperature would increase. Good. So if a chemical reaction involves a net release of energy, the observation you'll find is a temperature increase. On the other hand, if a chemical reaction requires more energy than it started with, if there's a net energy intake, the observer will find what? An increase in temperature? Remember, that energy is being put into these bonds. So when we have to put energy into those bonds, it's now not in the environment. So if we used to have more energy in the environment and now we have less, the temperature will have gone down, right? Decreased. So these are the two broad categories of reactions we can talk about. So let's look at two examples. Burning sugar. You've probably seen this demonstration in grade 9 science or maybe in grade 11 biology where they take sugar and add an oxidizing agent and burn it. No?
No.
Monday. Don't let me forget.
Yay.
Remind me Monday. It's a fun one. You've really never seen that?
No.
Oh, it's great. I don't even want to spoil it for you, but we'll talk about it. What's the chemical formula for sugar? Come on, all you biologists. Like, we'll say glucose, just to make it easy. Yeah, we'll say glucose, just to make our lives easy. C6H12O6. Very good. All right, we're going to burn it. When we burn something, what's it react with?
Oxygen.
Oxygen. Good. And when we burn a hydrocarbon, what are the products? The simplest possible products. Let's say we burn it completely. We get full and complete combustion. Carbon dioxide, and that'll take care of all the carbon.
Water.
And water. That'll take care of all the hydrogen. And can we quickly balance this? How many of these am I going to need? Good. And how many of these will I need? Yeah, 12 total. And I can get that by putting a 6 in front. Hey, how many oxygens over here altogether? There's 12 there and 6 for a total of 18. How many do I have over here right now? 6. So what do I need to do here? That would give me 16. So I'm going to multiply it by 6. Good. There we go. All right. So that's the chemical equation we are used to. But let me ask you this. Is it not true that we also make a whole lot of heat? Yeah, you have to put a little bit in, though you don't have to put a little bit in. That's actually not even true. When I show you the demonstration on Monday, I'm not going to heat it up to burn it. I'm going to use a little bit of sulfuric acid, and that will cause the chemical reaction to start. So we will give it no heat to begin with whatsoever. No new heat. And it will make a whole bunch of heat, right? You can imagine this. If you took sugar and burned it, if I then said like, hey, put your hand on that, would you?
No.
No, because it would be really, it'd be really hot, right? It wouldn't be safe. Maybe wait a bit. Also kind of gross. And since I use sulfuric acid to start it would also be really acidic. So it would burn you in 2 ways. Yeah, no, not good. Does that make sense? So this reaction involves the release of heat. And when heat is released, we call this an exothermic reaction. Exo is a prefix that means outside. So this releases heat to the outside. Heat ends up outside of the chemicals. An exoskeleton is an animal whose skeleton is on the outside.
Like people.
Yeah.
It bothers me that you didn't do the last 3 letters. I mean, I just don't know.
In my imagining, only the I was lowercase, but okay.
Well,
That's okay. All right. So there we go. Burning sugar is an exothermic reaction. We put heat energy out into the environment. The temperature around would increase. So surrounding temp, not even just surrounding actually, we can just say temperature increases. Temperature goes up. Temperature of the whole system will go up because energy that used to be stored in chemical bonds is now released into the atmosphere. And again, can't stress enough, where that heat energy comes from, the bonds. Bonds contained energy. When those bonds were broken, that energy was released. And it takes more energy to make the bonds of a complex molecule like glucose than it does to make relatively simple molecules like carbon dioxide and water. So that leftover energy gets stored as heat, or not stored as heat, rather gets released as heat. All right, on the other hand, photosynthesis is not exothermic, it is endothermic. Hey, what's the formula for photosynthesis again? It's already up here. What do you just have to do with the reaction we made? Flip it. Photosynthesis is just the opposite of burning sugar. Plants make sugar, and then we burn it. And they're just completely opposite reactions, right? You learn that in grade 9 science. They're the exact same operation in reverse. This is what we do inside of all of our cells to produce energy that we can use. Then we have a little molecule called ADP, adenosine diphosphate, which has been trained to absorb that energy and become something called adenosine triphosphate, and it can actually store that energy again, this time in something the cell can use really quickly. But literally, inside all of your cells constantly, sugar is being burned. Like when we talk about burning calories, that's not a euphemism. It's actually what's happening.
Just like you're on fire.
No, it's like sugars are burning inside of you. You yourself are not on fire. That would be problematic. If you catch fire, you should stop and then roll. Very good.
It's a terrible idea. If you catch fire from the inside, stop dropping and rolling isn't going to help. It's actually probably going to do more damage. You'll spread the fire.
Drown
That's a better idea.
Drown yourself.
Just to be clear, you are not going to catch fire internally. That's not going to be a thing.
Spontaneous combustion.
All right. So even assuming spontaneous combustion is a real thing, and I know nothing about this, I'm pretty confident that it would not be like the internal systems of your body exploding from the inside out. I am no physiologist, but I'm pretty confident that's not what we're talking about here. Now, in this case, when we want photosynthesis to occur, we take carbon dioxide, we take water, and we put them together to make sugar and oxygen. Where does the heat go here? Yeah, the heat energy is required here, obviously in the big space I left. And keep in mind that, like, when plants use sunlight to make photosynthesis, that sunlight doesn't then heat up our environment, right? Does that make sense? Normally, the sun shines down on Earth and it increases the temperature, but the sunlight that's absorbed by a plant to make sugar, that doesn't become heat because that heat is absorbed by the plant to fuel this reaction. This is endothermic.
Oh my God, I have this in grade 9.
Remember that if you have an endoskeleton, your skeleton is on the inside, like us, or the Terminator. Endoskeleton. And in this case, fine, I'm sorry, Zach. I know what you want, which is for me to make the dot on my eye a little heart. And you're welcome. Now I've done that. And if you note, right? You can't see it on here, but I even put the little white space, like to be like the little glow. Can everyone see that?
Yeah.
Okay. Just enough work.
That's your
Because you need to
Valentine's
warm up
Day.
inside, right?
Now, that's right. This reaction would be observed as a temperature decrease to the system. We are reducing the heat in the system because that heat energy is being turned into chemical energy. Now, a little later on in this unit, we are actually going to carry out chemical reactions inside a device that can be used to measure how much heat is made or how much heat is lost. It will either be a really nice professional looking calorimeter, or if I can't find them, which currently seems possible, it may be a whole whack load of styrofoam cups with styrofoam lids. Who knows? Sky's the limit. But one way or the other, we're going to use a device called a calorimeter, which looks basically like this. Now, this is a fancy one with a motorized spinner to stir the liquid and everything like that. Ours, or to stir the air rather, which will probably, we are not going to be quite so high tech as this beautiful bomb calorimeter. Yeah, that's what they call it. Yeah, we could make one. We're not going to because this isn't a manufacturing class, but a bomb calorimeter just means that you have an isolated chamber inside and it's surrounded completely by water, because water is a really good way to absorb temperature, to absorb energy and measure temperature changes. And so you can very, very, very reliably tell how much temperature has been changed by the reaction. My best friend works out of the University of Ottawa. He's a physiologist. And they have the world's largest human-sized bomb calorimeter, where they have a device like this that's actually big enough that they can put somebody inside a chamber that is then surrounded by an insulated space with water in it. And so you can do things like exercise, and they can actually measure exactly how much energy you've given off in the process, like your exact energy utilization, which is pretty crazy. When he was still at Brock, I used to do some of his physiology experiments. I'd sign up, and they were uncomfortable experiences that I'd like to never repeat. But it looks like this. Okay, so to do this, we're going to get to chemistry. But before we can get to chemistry, we have to get a little bit of physics out of the way. And that's what today is about, which is this. When we go to measure temperature change, we're going to measure that using what device? A thermometer, all right? We may use a calorimeter, we may use a paper cup, but the actual temperature change we will measure in using a thermometer, and we'll measure it in what unit? What unit does a thermometer give us? The ones we have. Celsius. And maybe if we feel so inclined, we'll convert that to Kelvin, but still those are units of temperature. But I'm not actually interested in temperature, not in the long run. I'm actually interested in energy. And we don't measure energy in Celsius, we don't measure energy in Kelvin, because Celsius, Kelvin, temperature, all of those measurements tell us the average energy of an individual particle. That's what Celsius is. Celsius says the average particle in there, how fast is it moving? What I want to know is the total amount of energy. Think of it this way, and we probably talked about this in grade 11. What has more heat, an iceberg or a hot cup of coffee?
Iceberg.
An iceberg by orders of magnitude, right? Even though it's colder, even though every molecule in that iceberg is a lot colder, has a lot less energy than every molecule in that coffee cup, there's just so many of them, right? There's just so many molecules in an iceberg that summed all together, they have a lot more heat, even though their temperature is much lower. Does that make sense? Heat and temperature aren't the same thing. Temperature is a measure of the average heat of an individual molecule. Temperature is a measure of how much energy overall. And to do this, we have to understand that different things are able to absorb different amounts of heat without changing temperature. You know this instinctively. If I am going to take a hot pan out of the oven, what do I put on? Oven mitts. What are they made of? Like some kind of cloth material, right? Would I be smart to take those oven mitts and run them under water and then take the pan out of the oven? No, because water heats up a lot quicker than oven mitts. The wet oven mitts get very hot very quickly. Has anyone ever had that happen to them?
No.
Oh, I have.
Why?
Because I used to work in a restaurant and things get wet and you got to go in the oven quickly and people shout and yell and it's very traumatic and then you get burned. So different things. Now, would you put plastic gloves on and take something out of the oven? No, that would be unwise, right? Likewise, my Contigo coffee mug over there is amazing. If I remember to take it home one of these days, you can put coffee in it at 6 a.m. and at noon it's still hot. My Tim Hortons coffee cup, yeah, it's amazing. Best thing I've ever, probably my favorite purchase of the last decade. And it was like $11 at Costco. But those Contigo coffee mugs, they're amazing. My Tim Hortons coffee cup, not so much, right? I put coffee in it, 20 minutes later it's cold. So different materials require different amounts of heat energy to change temperature. That makes sense? And we measure that using a measure called specific heat capacity. Hands up if you've done this in physics. We got one. Anyone else? Okay, so we'll talk about slowly. Specific heat capacity is this. It is a measure of how much energy it takes to change the temperature of a material. Now, what do we measure temperature in? Celsius or Kelvin. And if you're talking about changes, they're one and the same, because 1 Kelvin change is the same as 1 degree Celsius change, right? One and the same. So we're going to change temperature based on how much energy we put in. What do we measure energy in? Joules, okay? So specific heat capacity tells us how much energy, how many joules of energy it takes to change 1 gram of a material by 1 Celsius or 1 Kelvin in temperature. And sometimes we do it not in grams, but in kilograms. All right, 6 of one, half dozen of the other. The chart I've given you here uses kilograms. So specific heat capacity is how many joules are required to take 1 kilogram of material and change it by 1 degree Kelvin, or if you prefer, joules per kilogram per degree Celsius. As long as we're talking about change, Kelvin and Celsius are the same. Okay, now, you guys, at least if you took chemistry with me, you know all about dimensional analysis, right? Remember that? Okay, so here's what I want. I'm actually curious for, can we make an equation that would tell me how many joules of energy it takes to do something? Say I had, I don't know, 20 kilograms and I want to change its temperature by 30 Kelvin. And I know its specific heat capacity in joules per kilogram per Kelvin. What could I multiply this by so that I would know just how many joules of energy are required? Well, let's take a look. I'm not looking at letters here. I'm not asking, do you remember vaguely something you were taught by someone else? I want to work our way through it. With these units here, what would I have to multiply this by so I'm left with just the joules of energy? Give me one thing I'd have to multiply it by. Good. If I multiplied this by kilograms, then kilograms would cancel with kilograms, and now I would have joules per Kelvin. What else do I need to multiply it by? Kelvin. And then I would have just joules. So what did I multiply this by? And kilograms is a measure of what? Mass. So we multiplied by mass, and we multiplied by temperature, not heat. Remember, Kelvin, Celsius, they don't measure heat. They measure temperature. And those are two distinct and different things. Heat isn't temperature, temperature isn't heat. You can have a really high temperature, but if it's a small little sample, not a whole lot of heat. You can have a really low temperature, like an iceberg, but you still have a lot of heat in there because the thing's massive, right? And so what we end up with is this. If I want to know Q, which is heat energy, I could take this C. Oh, that's not C, that's an N. I could take this C, which is what we talked about here, the specific heat capacity. Which we measured. We said it's how many joules it takes to take a kilogram of this stuff and change it by 1 Kelvin or 1 degree Celsius. And you said all I have to do is multiply it by what two things? Yeah, I had to multiply it by the kilograms, which is a measure of mass. So we multiply it by mass. And then we have to multiply it by, yeah, and this is the change in temperature, how much the temperature is changing, right? How do we denote change in science? Delta. And what letter do we use to denote temperature? T. Now, would that be small t? What does small t represent? Time. So it would be big T. And this is the equation. Q equals mc delta T. M is mass, and we are typically going to use kilograms. Yes. Mass is denoted by a lowercase m. Uppercase M is used to denote the molar mass of a compound, right? So like potassium has a molar mass of 39.0983 grams per mole. That would be denoted with an uppercase M. Lowercase m is the actual amount of mass you have of a real subject. That's right, and a capital delta. This is the change in temperature. Note, this whole equation is about changing temperatures. It is not, you cannot use this to calculate how much heat something has at a certain temperature. It is all about change in temperature. And we measure this in Kelvin or degrees Celsius, because when we're changing temperature, changing by 1 Celsius is the same as changing by 1 Kelvin. That makes sense? Because of the delta, it doesn't matter if you use Kelvin or Celsius. This is a lot easier if we just do an example. Yes, ma'am? No. I mean, you could, it would. The absolute zero thing isn't a problem for this because we're talking about changes, but all of the C values would be different because a change of 1 degree Celsius is the same as a change of 1 Kelvin, but a change of 1 Fahrenheit is a lot less than that. That makes sense? So the reason you can use either here is when they came up with the unit Kelvin, they said, let's make the steps the same. A change of 1 Kelvin is still going to be a change of 1 Celsius. All they changed was the 0 point, where they took 0 from being the temperature at which water froze and put it down to the temperature at which all things stop, which is negative 273.15 Celsius. They made that 0 Kelvin. Okay, so let's actually do a question with this. If I have 500 milliliters of water in an electric kettle, and I raise its temperature from 25 degrees Celsius to 65 degrees Celsius, how much heat energy flows into the water? So the equation we're going to use is that heat is equal to the mass of the subject times, what does C stand for again? Specific heat capacity, which tells us how much energy it takes to change the temperature of that object, and then times the change in temperature. So let's take a moment and look at the side here. Do we know the mass of water here? Do we?
Yes, water is the density of 1.
Oh, yeah, he's right. This is going to be my big moment. Do we directly know? Has the question told you the mass of water? No.
Yes.
We know that we have 500 milliliters of water. And this is something that you're going to need to know. Pure water has a density of 1 milliliter equal to 1 gram. Convenient, right? And to be clear, that's actually only true at a certain specific temperature. But it is accurate enough for what we're doing here at all times. So pure water, every milliliter weighs 1 gram, which means how much water do we have? 500 grams, good. So we have 500 grams of water. Those of you who took chemistry with me before, you know that I like units to not only have the unit, but what we're talking about. Yes. What is the specific heat capacity of water? You're going to have to check the table up above. Let me know. $41.86. Perfect. So 4,186 what? 4,186 cats? 4,186 blueberry muffins? Yeah, is this one kilojoules? No, this is measured in joules. Yeah, good. Okay, so yeah, because you're used to 4.186 from physics. Yeah. So 4,186. What's the unit? Joules per Kelvin times kilograms of water. Sorry? No, order doesn't matter in multiplication. In fact, that's consistent with what was above, right? So kilograms of water and times Kelvin. And what's our change in temperature? Yeah, how'd you do that? Yeah, remember delta by definition, change always means final minus initial, right? That's what change means. If you want to know your change in height from when you were born, you'd take your height now, you'd subtract your height when you were born, and that would give you the change. So change in temperature, 65 degrees Celsius minus 25 degrees Celsius, and that equals 40 degrees Celsius. And that equals 40 Kelvin change, right? Again, you can only say that when we're talking about change in temperature. Otherwise, obviously, Kelvin and Celsius aren't the same. But this is a shortcut where we don't have to convert both units to Kelvin because they'll both change by the same amount, which would cancel when you subtract them out. Okay, I believe that I am ready to use this equation and everything's going to work. I'm going to say 500 grams of water times, what was C? 4,186 joules per kilogram of water times Kelvin times 40K, right?
Well, when you say it like that.
No, we're good, right? So go ahead, do the math. Tell me what we get. Right?
Oh, wait, I've seen what it is. Okay, yeah.
What do you mean? Multiply. How are we supposed to do the math? You take this number, you multiply it by that number, then you multiply it by that number, and we'll get a number. I bet we can do this in our head. 500 times 4 would be 2,000, so 500 times 40 is 20,000 times 4,000. So we're going to be on the order of like 8 million plus that doubled. So this should be 8.372 million. 8.372 million.
You were actually pretty close.
How'd I do?
You got some of the numbers right.
Hey, there we go. So there we go. So that's right, yeah? Use your calculator, do it. Why can't I? I just did.
Don't do 500.
What's not the same unit? Well, sure, what do you mean all of them?
Well, they're all on different units.
Kelvin cancels with Kelvin.
But you can't cancel Kelvin.
Aha! What can't I cancel? I can't cancel kilograms with grams. So this, I need to make sure I convert to kilograms. So if that's grams, if I want to cancel grams of H2O and instead get kilograms, how many grams are in a kilogram? 1,000, right? Kilo means 1,000, so 1 kilogram is 1,000 grams. Now, the simple thing is we just slide the decimal place over 3, right? If you're comfortable with metric, but if you're not, divide it by 1,000. What do we get for the mass? 0.5 kilograms. Very good. And now this is, of course, just nice and easy. We should get 8,283,720. Yeah? Jules, is that true? And I should put kilograms of water here. That will cancel with that. The only unit that remains is joules. Okay. So there we go. The takeaway, make sure all of your units whatever units you use in C, you have to make sure you use the rest of those units. So if you looked up an American textbook and it gave all of these in pounds and Fahrenheit, then you would need to make sure that all your masses were in pounds and all of your temperatures were in Fahrenheit. For the record, scientists in the States also use IUPAC units, and they would also use kilograms and joules. But
Are we worried about?
yes, we are. See, you're stealing my thunder, and I love it. We do care about significant digits. I was going to talk about tomorrow. If you really want, how many significant digits would we actually have in this answer? I'm seeing just one, right? Just here. But I was going to do a reminder on significant digits tomorrow. But if you are feeling very, very, very specific, this should actually be 8 times 10 to the 10 to the 4 joules. That's true. That's a better answer. if we're concerned about significant digits. If that doesn't ring a bell to you, significant digits, that's okay. We are going to talk about it. Is there anyone who has no idea what significant digits means, like you've just never done it? Don't worry about it. We'll talk about it tomorrow, and you'll be all over it. For today, don't worry about it.
Pardon? Yeah, that's it. I've never tried. When? Is it?
No.
What?
Oh yeah, I remember walking into your class.
She's done it if she's been with me.
It's like the old math teacher thing. My favorite one of all time was I taught. Do you know Wally Aprendick? He's a physicist.
Yeah,
He's a great guy.
Yeah.
So Wally and I taught together at South Lincoln, and he was great at physics. Wasn't so much comfortable with biology or like the climate change stuff in grade 10.
Yeah.
So when he was teaching grade 10 science for the first time, he said, I don't love these 2 units. And I said, you can use my stuff. Yeah. So I gave him, and we were right next to each other classrooms. So every day he'd use what I taught that course with, all the stuff. So funny, the next year I had all these kids in grade 11 bio, and they were like, oh, I swear to God, Oprendick never did that last year. And I'm like, listen, I fed him his lessons every day. Yeah. I know exactly what he taught. Like day by day by day, I can tell you.
In chemistry, there's a slide. Maybe it's just
anyway, don't worry. I'm really finicky about it, so we will spend a whole day on it, and then it'll be like.
It's not that hard.
No, it's like riding a bike. You'll be fine. You fall a couple times, then you get it, then you can do it forever. Yeah, do you have to ask me that? You don't have to ask me that.
No, probably right. We don't spend a lot of time on it.
Okay, my friends, I want you to try this one. Same equation. Try it out. We've got a 50% ethylene glycol solution. This is the coolant. This is the coolant that they use, like in industrial cooling products, right? So, like if you visit a brewery or a winemaking, and they've got these big the big stainless steel brew containers that have these metal jackets that chill them from the outside. It contains ethylene glycol, and I'm giving you its specific heat capacity here. Watch for units. There's no guarantee of, if I give you a C value, make sure you watch the units. All right, and I'm asking what temperature change would be observed if 4 kilograms of this stuff absorbed 250 kilojoules of heat. Yes, sir.
So, is 50% at all relevant?
Nope.
No?
Nope. This is the thing. This is its specific heat capacity. I mean, the 50% just means that this would be ethylene glycol mixed with water at 50%, but this is its specific heat capacity. So take a minute, try it out. I'll walk around, and then we will take it up. That is C, right? Because it's joules per gram, 3 Celsius. That's specific. But you're right that I'm giving you heat. Yeah. Dot Q, dot C, what else do I need? M, what am I asking you to find? Watch those units. Converted to joules. I want to see those units. As you have it written here, the answer right now is in joules per gram, right? Which is not what you want. And I know that seems pedantic, but just believe me, when you get to a point in chemistry where you're doing big, long, complicated calculations, having the units written down will prevent you making mistakes. Yeah. Doesn't matter. It's kilojoules.
Times by that.
But we wanted 20 people.
You're right. So which is kilo?
It's times by 1,000, it's divided by 1,000, which means they'll be.
Oh, you're thinking backwards.
Oh, no.
It means it's 1,000 of them, so you need to
Times by.
times by, right? Because there's 1,000 joules.
The answer.
I think that, look, guys, kilo is a universal thing. Kilo just means how many of something? 1,000. You could count in kilo squirrels if you really wanted. I feel like there's about 4 kilo squirrels in my backyard every day right now, eating from my damn bird feeder.
What's the one?
And I've been catching them in humane traps and driving them across the river to the other side of Port Dalhousie and then releasing them into the woods. And I swear they're just coming back with all the woodland friends. It's like party time in my backyard and all the squirrels invited. And then now the cardinals are coming in and like dive bombing them and like fighting over the. It's like
Actually,
a
we
war
don't.
zone, man. It's ugly.
It oddly felt perfect.
Well, my dog, it's my dog chases them, and my dog actually made contact with one the other day. I realized what a complete wuss my dog is. So the squirrel went and didn't see. I still have like my snow fencing up, just like chicken wires. And so the squirrel ran and like bounced off this thing, and my dog like literally got a snout full of squirrel and was just like, "Oh." And the squirrel ran off. It had no idea what to do. I thought it was hilarious. Anyway. All right. Nice. So, good. Put them in. That's all. Put them in. That's all.
Do we need to change the joules?
Of course. Your C is measured in. Yeah, you gotta make sure units all match up, otherwise they won't cancel. So the trick is you could change C. Changing C to me is stressful because there's like fractions and nuts. So to me, use these as your base, make sure everything matches it. Though you wouldn't be mathematically wrong if you change C, after everything else is the same. It's not how I do it. So in this case, it would actually make your life easier. As a rule, pick a strategy and stick with it. Yeah.
Answer right.
But looks good. Definitely the right order of magnitude, right? Because you're basically taking that and dividing it by just shy of like 1.5-ish, like 15,000-ish. Should be about 100 equivalent. Yeah, that makes sense. Something like that. How we doing? That is this was good. So you've got to turn this into grams. So raise it here, go back here, and say, okay, if I have 4 kilograms, how many grams? That's right. That's exactly right. That's very good.
Point of view.
Okay, yeah, give me a sec. We'll double check it all together. Good. Okay, that's not C though. You're right that we're talking that, but kilojoules is a measure of the energy. Which letter is that? Oh. Which letter is that?
4,000.
Heat energy is change in temperature. What's heat energy? Q. Good. So since I've given you the energy, that is
We want this to be
good. And the only thing to watch out for, just like you made this kilograms into grams by multiplying it by, yep, kilojoules, we need in joules, so we're gonna have to multiply this by. You already did here. Kilo means Yep, so this is kilojoules, so we have to multiply it by 1,000. Just because our C isn't measured in kilojoules, this C is actually measured in joules. Does that make sense? So you always just have to watch and make sure you match that unit. Yeah.
We're timesing, let's make it both kilojoules and.
You could do that if you want. That's not what I would do.
No, you would.
My rule of thumb is just make your units match C. Don't change C, match to C. Though mathematically, what you just suggested totally works, totally right.
Yeah.
Nothing wrong with it, just not what I'm going to do. I am going to put C in there and then make my other units match to it. But it's mathematically identical. And in fact, yours is easier because what you just go because you've divided by 1,000 and multiplied by 1,000. It just doesn't change. But
Yeah, we'll change them.
no. Do it your way. Who am I? What am I? Gosh, have I taught you anything?
Yeah.
You don't blindly follow authority. Do it your own way. See what answer you get. Trust yourself. I trust you. Well, I trust you. Seriously, don't bend yourself to my will. You have an interesting idea. It's a good idea. Do it. Worst case scenario, you're wrong. Best case scenario, you proved you had an independent understanding of something instead of blindly following me like a sheep. Now do it. Try it. Figure out. See what happens. Okay. And while Zach Brown is trying his creative method, which should work perfectly, and I have faith in him, am I rushing you guys if I take this up right now? All right, let's give it a try. So the equation we're going to use is Q equals MC delta T. Okay, so let's take a look at each of these things and see what we already know. Maybe I'll leave myself a bit more room in case I need it. Okay, let's go through and take a look at these. Specific heat capacity is 3.5 joules per gram Celsius. What is that? What is it? Very good. It's say. So we would say 3.5 joules per gram per degree Celsius. Now listen. My advice would be, once we have this, make everything else match it in units. That's going to be the most consistent, easiest way to do this. So do I know delta T, change in temperature in Celsius? I don't know that. In fact, that's what I am trying to find. But we don't know delta T. Do I know the mass? Okay, as given, what's the mass? 4 kilograms. Do I like that as given? Because I want it to be? Yeah, and so I would say, I don't want kilograms, I want grams. How many grams are in a kilogram? 1,000. Now again, do you have to show me the dimensional analysis here? Not for a simple unit conversion, though if you're the type who tends to mess these things up, show it. Not going to hurt you. So 4 times 1,000 is? So we have 4,000 grams. All right, what about Q? Do I know? I must know Q. If I'm going to be able to solve this, I can't have two unknowns. Good. And remember, Q is a measure of heat energy. So what I know is that I've pumped 250 kilojoules of energy into this thing. Now, do I want kilojoules? I want joules. So I'm going to put joules up here, kilojoules down there. What fact makes this through? How many joules are in a kilojoule? Like that. And so this is 250,000 joules. Some people asked, could I just change the units in C? You could, absolutely. You'd multiply by 1,000 to make the grams into kilograms, and you'd divide by 1,000 to make the joules into kilojoules. That works too. My preference is make everything match C. All right? If what I just said confused you, completely ignore it. Now, you can plug your numbers in right now, or you can rearrange the equation first. It doesn't make a difference. What do people like to do? You want to rearrange the equation first? What am I trying to solve for? Yeah, delta T. D actually is different. D is instantaneous. Well, it's the instantaneous rate of change, but we're not talking about that. We're talking about overall rate of change, delta. So if I want to get this by itself, what am I going to have to move? So I'm going to have to divide by M so it cancels. I'm going to have to divide by C so it cancels. If I divide that side by M and C, I have to divide Q by M and C. I want to note, if you put the numbers in first and then divided, that's Just as meaningful. Nothing wrong with that. But my equation ends up being delta T equals Q over MC. And now I can just put my numbers in. Delta T is 250,000 joules divided by 4,000 grams and 3.5 joules per gram degrees Celsius. All right, shut up. Joules cancels with joules, grams cancels with grams, and we'll be left with degrees Celsius. And when we do this math, what do we get?
You get 20.
Those of you wondering, my grandfather is still curious whether there's been a baby or not,
They had that random-
and there has not been.
I like how you text every time you text me. Yeah, what did he say?
No. So it's interesting. The first is my voicemail texting me to say I have a voicemail, which I must have thousands because I've never once checked my voicemail. And then the second one is from my grandfather. 17.857, blah, blah, blah. Now, if we were being really finicky about this, how many significant digits am I given? Just one. So if we were worrying about significant digits, again, if you don't know this, don't worry. We'll talk about it tomorrow. This is a 20 degrees Celsius shift, give or take. 2 times 10 to the 1. Yeah, I'm just going to write 20. But if you, for today, just put the answer. Round it where appropriate. Questions about that? Comments, thoughts, hopes, concerns, prayers? All right, you probably have time to get the next one done. Try that. For tomorrow, I want all the questions on here done. All of them.
For tomorrow.
Yeah,
Yeah.
tomorrow.
It's tomorrow.
I'm coming. I'm going to knock on every one of your doors.
I'm
I'm going to say,
Just go to St. Catherine's.
give me your homework. Hand it over. That's the voice I'm going to use. All right? Oh, that was good. It's the homework you deserve. So anyway.
If you don't show up for Batman.
Listen, nobody wants to see me in a Batman costume, including me, most conspicuously.
One of my aunt's wedding, you can be Batman.